Reflection contrast microscopy, the bridge between light microscopy and electron microscopy.
Dus de Frans Prins is toen samen met iemand die met mij promoveerde op reflectiecontrast. Die hebben toen samen gewerkt aan de reflectie van EM-apparaten. En dat hebben ze heel uitvoerig gedaan. En toen hadden we natuurlijk iets ideaals. Toen hadden we prachtige beelden van preparaten die maar 90 angstrom dik waren. Dat had toen natuurlijk nog nooit iemand iets gezien.
Compared to conventional bright field microscopy, reflection contrast microscopy is a light microscopy method to image cells at high definition and enhanced sensitivity. RCM images have a very high contrast, which makes them easily applicable for digital image analysis. Since ultra-thin sections are mostly used in this method, RCM has a function in bridging light microscopy with electron microscopy. RCM can also replace electron microscopy for rapid and simple screening of large quantities of immunohistochemical stained samples. Special attention is paid to small biological objects that have to be processed for RCM. If you encounter the limits of bright field microscopy, the resolution, sensitivity or handling of specimen, RCM can be a feasible option. RCM uses slightly adjusted EM methods for specimen preparation. Therefore, many familiar techniques for ultra-thin specimen preparation can be applied. It is of great importance that the embedding medium has a refractive index similar to that of glass. Low-acryl and EPON are widely used examples. Ultra-thin cryosections can also be used. Reflection contrast microscopy can be used as a bridge between light microscopy and electron microscopy. It visualizes ultra-thin sections with an image definition normally obtained by using electron microscopy. The main advantages of RCM over bright field microscopy are increased sensitivity and better image definition. The theoretical resolution of light microscopy can be reached in RCM. Compared to EM, RCM is a better tool to get an overview of a section. For instance, immunostaining can be detected at 500 to 1000 times magnification and makes it possible to localize the labeled sites. RCM can be used as a guide in a study of ultrastructural localization of beta amyloid. RCM is a suitable method to study very small biopsies, which could formerly only be analyzed by EM or immunofluorescence. With RCM, images can be made of any object with a refractive index different from glass. A special feature of RCM technology is the use of 50 to 100 nanometer sequential ultra-thin sections, which allows us to use RCM image as a localization tool for EM. All types of specimen prepared for EM can also be used for RCM. The main difference between RCM and EM is that a glass slide is used for RCM and a copper grid for EM. Only plastic embedded or ultra-cryo sections and whole cell preparations are suitable for RCM. Generally, the normal 4 micron sections are too thick for RCM and result in blurred images. Studying living cells was the first application for RCM. In an aqueous environment, the cell glass contacts are the less reflective, darker contact sites, so movement can be studied. RCM is performed on a microscope with incident light instead of transmitted light. RCM images can also be produced with a fluorescence microscope adapted in such a way that only the reflected light from the surface of the specimen forms the image. The microscope configuration of RCM is a combination of two contrast-enhancing components, the central stop module and the anti-flex component. The central module contains a central stop and aperture diaphragms and are located in front of the lamp house. Passing this module makes the light beam ring-shaped. The anti-flex component consists of a set of crossed polarizers, a so-called pole block, and a quarter wavelength plate, which is located at the front lens of the objective. It functions as follows. The light is linearly polarized by a 0 degrees polarizer, deflected by the 50-50 reflector in the vertical light path. Upon passing the quarter wavelength plate, the light is circularly polarized. After reflection from the object, the light passes the quarter wavelength plate and is turned by another 45 degrees. Related to the incident ray, the polarization state has turned 90 degrees, so that this light can pass the analyzer, which is at a straight angle to the polarizer. Consequently, it will reach the eye. All internal reflection is stopped by the analyzer. Image formation in RCM is based on both reflection and interference of reflected light rays. Instead of the use of the central stop module, a right-angle prism can be used, which is glued with a drop of oil on the reverse side of the object glass. A diamond knife is used to cut ultra-thin sections. A ribbon of section is placed in a water bath. For sequential EM and RCM, the sections are isolated in pairs. Then a pair is split into single sections. The first section is placed on a grid by carefully placing the grid under the section and slowly raising it at a slight angle. A platinum wire loop is inserted beneath the second section, raised with the section in the center of the loop, and placed on a clean microscope slide. The section is dried on a hot plate. Sections are encircled with water-resistant ink on the reverse side of the slide. Sections for morphology interpretation are counterstained with light green, toluidine blue or acridine orange. Rinse the excess stain with distilled water and dry on a hot plate. Immersion oil can be used as mounting medium. The slide will be covered with a clean cover slip. Put a drop of immersion oil on the specimen and center it, using a low magnification objective. Change to the anti-flex objective, locate the specimen and focus. Here we show many types of RCM applications and disciplines in which RCM has been used.